Not because they are easy, but because they are hard.
I know if you go on to Math 110 at least, you're going to have to be able to find points of intersection of two graphs, whether they're lines or parabolas or whatever. So I'm going to go over it.
Allow me to demonstrate.
Let's get right to a problem, and then we'll review kind of what we did. Okay, I've got two equations here.
I know that, dude.
And these ones happen to be lines. They're going to intersect in exactly one point in this case. Now, other type of graphs may intersect in more than one point, but in this case we're looking for one point, and remember that one point has two values, an x and a y. So we'll start off by solving one of the two equations for one of its variables. You get to pick whichever one you want, whichever is easiest. Now in this case, I think the blue x is the easiest because it's already solved for x. Okay, so I'm going to choose the blue x, and then I'm going to do step B, and that is to substitute the expression equivalent to that variable, 3y, into the other equation. I'm substituting it instead of x. When I say the other equation, I hope you know I'm talking about the green one. So let's substitute 3y instead of x into that green equation, and we'll get an equation
That's just crazy enough to work.
with only one variable, only y, which we can solve for. 3y plus y is 4y. If 4y equals 20, and I divide both sides by 4, I know y is 5.
Is that your final answer?
Well, remember, I'm looking for a point of intersection, and a point has an x and a y. So I'm kind of halfway there, because I found the y, but I still have to find the x. So but I have more information now, you see. So what I'll do is take the value of y, which is 5.
Excuse me?
Take the value of y, which is 5, and substitute it in to the original equation instead of y. So instead of y, I'm going to write 5. And now I have an equation with only one variable, and it's the other variable, x,
Hey, this is great, man.
which I can solve. And x will be 15. So the solution to this system, if you would, more than one line, is the point where x equals 15 and y is 5, or sometimes we write the point 15, 5. Not so bad, and we did it without looking at the graphs, which is pretty cool.
Wait a minute.
Since I went to all that work, and I know this works in the blue equation, I just solved it,
I can do that, but I don't want
it
to.
would probably behoove me to check it in the other equation, the green one. Doesn't take much work, does it? Let's put 15 in for x and 5 in for y, and just make sure.
You are correct, sir.
And I know it works. In fact, I know this is the point where they intersect, because this pair works in both equations, and that's the only point that works in both equations, the point where they intersect.
What happened?
Well, let's go over what we did.
If we keep this speed, we'll blow up any minute now.
Pay attention. First thing we did was we solved one of the two equations for one of its variables, whichever was easiest. Then we substituted the expression equivalent to that variable into the other equation, and that created an equation with only one variable that we could solve, and we did that. We solved the now single variable equation created by step B. That gave us more information. It told us what one of the variables was, the value. So we substituted that value that we found in step C into either of the original two equations and solved for the other variable. And then don't forget,
I can do that, but I don't want to.
check your proposed solution. Check your x and your y into both equations. Make sure you didn't make a mistake. If it doesn't work in both equations, you haven't found the point of intersection. Okay?
Do that again.
Okay, this time, let's do it with two graphs or two equations that are not lines. The blue one is going to end up being a parabola, and the green one
I know that, dude.
is a line because it's of degree 1. There's no exponents. Okay, so we should have, well, we don't know how many points of intersection we'll have. We could have more than one, though, is the point. So, let's begin by solving one of the two equations, either one, for one of its variables. It doesn't really matter which. The green equation looks easier, and probably I'd solve for x, but I want to show you that there's no really wrong answer here. I mean, as far as which to solve for. So this time, I'm going to solve for y, just from habit. I'm used to solving for y. So let's see, I'll subtract x from both sides. And then, that's a negative y. I don't want negative y, I want y. So I'll divide everybody by -1, and y will equal x minus 1. That's the first step, to solve for one of the variables. Step B is to substitute the expression equivalent to that variable, which in this case is y. The expression equivalent to that is going to be x minus 1, and I'm going to substitute it into the blue equation. Instead of y, I'm going to put what y is equal to, x minus 1. Now that creates an equation that I should be able to solve.
Now what am I going to do?
Well, this is a quadratic equation because it has an x squared. But we know how to solve a quadratic equation, but we also know that we're probably going to get two answers.
Hey, that's just crazy enough to work.
Let's do it. If I distribute that -3, I get x squared minus 3x plus 3. Recall, a negative times a negative equals a positive. Now let's begin by getting a 0 on one side. So I'll subtract 1 from both sides, and I'll get x squared minus 3x plus 2 equals 0. Now remember, one way to solve a quadratic, if you can do it, is to use... Okay, so let's factor. And I see that there are two answers here using the 0 property. What do we make x equal to make this factor 0? That's going to be a root.
Darn tootin'.
One of the answers is that x equals 1. Now in this one, the other answer will be, what makes that equal to 0?
I'm dangerous. I'm very, very dangerous.
X equals 2. Now these are both x's. So it looks like I'm going to have 2 points of intersection. One of the x's will be 1, and the other x will be 2. Now I need to substitute, I'll do it separately, each of those x's into the other equation and find y.
I don't understand.
Well, since I have 2 points of intersection, I have to do 2 separate substitutions. So I'll put 1 in instead of x and solve for y. Subtracting 1,
Hasta la vista, baby.
I get negative y equals 0. And if I divide by -1, y is 0. So in that case, I end up with the point 1 for x and 0 for y. That's one point of intersection. If I put a 2 in for x and solve for y, let's see, subtract 2 from both sides and then divide by -1, I'll get y equals 1. So the other point will be x is 1 and, x is 2 and y is 1.
Oh, no!
There are actually 2 points of intersection between this parabola and this line.
Excuse me, Professor Brainiac.
Oh, almost forgot the last step. And since I've done twice the work, I'm going to have to check 2 answers into the other equations. Let's put 1, 0 into this. A 1 in for x and a 0 in for y. And I get, son of a gun, 1 does equal 1, so that one checks.
I'll make this look good.
In the other point, I put 2, 1. 2 in for x and 1 in for y. Let's see. 2 squared minus 3. 1 does equal 1. That one also checks. So I'm in good shape. They checked. So these are the 2 points of intersection.
And you're going to do it because I said
Let's
so.
check it into the original one also, just to make sure. 1, 0. 1 minus 0 does equal 1.
Well, your story is very compelling.
We're looking good. And 2, 1. Well, 2 minus 1, if we put that in, does equal 1. So guess what?
You just want to be...
No, but we did find the 2 points of intersection.
There's something I have to ask you.
Well, we have to look at this graph just to see. If we graphed this, of course, we'd have to solve for y first, this parabola.
I know you are, but what am I?
And that's what it would be if you solved it for y. And if we graphed it, it would look like this. Now the green line, of course, we'd have to solve that for y also, would equal x minus 1. And if we graph that,
To infinity and beyond.
that's where that would be. And guess what? One point of intersection is the point 1, 0, and the other point of intersection is in fact the point 2, 1. So it does work. We didn't need to graph it, but it's nice to see what's going on, isn't it?
Alrighty then.
So here's what we did in summary. We looked at the 2 equations. We solved one of them for one of its variables. Doesn't matter, whichever's easiest. Then we substituted the expression that that variable was equal to, or equivalent to, into the other equation. And that created a now single variable equation that we solved. When we solve it, we actually get a value for that variable. And then we substitute that value into either of the equations and solve for the other variable. And then finally, very important, after all that work,
I can do that, but I don't want...
check your proposed point. Make sure it works in both original equations. Don't forget, there's another way to check your points of intersection that you found.
Now I use my secret weapon.
Your calculator. If you turn this baby on and graphed or inserted the functions that you put in, first we'll put y equals, get rid of something that you used before, and put in that quadratic. And don't hit graph yet. Go down, because remember you can graph up to 7 of these things. Hit the down cursor. Clear out anything that may be in there. And then put in the linear equation, x minus 1. Now you can graph and see the picture, but then you can also hit the trace button and move left or right and move on to the points of intersection and see, in fact, at least approximately, that they are the points that you think they are.
Take off, eh?
Okay, and you can clear to get out. If you want to get a more accurate answer for this point of intersection,
Are you pondering what I'm pondering?
you may want to zoom in and then trace along it to see what the points of intersection are. Or
Wait a minute, 99. That gives me an idea.
you can let the calculator assist you in being even more exact, and that is using the calc key. Remember that second trace
I'm dangerous. I'm very, very dangerous.
second trace yields calc. So if you have these functions already inserted into your calculator and you hit second trace, choose number 5, intersection, and then it'll ask you what's the first curve, and either move on to that first curve, but it'll probably jump onto one, and hit enter, and then move on to the other curve or the other equation and hit enter, and then move near one of the points of intersection. That's why you need to make a guess. It wants to know which point of intersection you want. So cursor over very close to the point of intersection and hit enter, and son of a gun, the calculator will tell you exactly where that point is, or at least out to as many decimal places as you have it set. Okay, well, it's time to go do your homework, so
Take off, eh?
get to it.